Okay, hello friends. In this video, we'll be discussing the further part of it. In the previous videos, we have learned about Jacobin matrix. We have learned about chain rule in the vector field. Today, we'll be learning something more about scalar fields. In unit number 3, we have introduced you all with the vector fields, right? We have learned what the vector field is, when it is differentiable. Also, we know that it is differentiable implies it is continuous. We have learned about a Jacobin matrix. Now we will concentrate again on some application of what we have learned in the scalar field. Okay, so we come back to the scalar field. In the first thing that we learn in this unit about the scalar field is nothing but an Hessian matrix. Okay, so let me just state this statement what I have wrote. Suppose f from Rn to R be a scalar field such that all second partial derivatives of f exist and are continuous over the domain of the function, then the Hessian matrix, which is denoted by HF, this means it is a Hessian matrix for f, it is a matrix, it should have some dimension, right? So we know that if I just talk about the Jacobin matrix, if my f is from, suppose if I write it here with the pencil, that if my f is from Rn to Rm and I am supposed to find out the Jacobin matrix, that is denoted by df, will going to be nothing but an m cross n matrix, right? So in terms of a Jacobin, we know it is nothing but m cross n if the function is from Rn to Rm. But when we talk about Hessian matrix, my function is a scalar field which is from Rn to R, then the Hessian matrix is an n cross n matrix. Okay, just note it down. So my Hessian matrix will be an n cross n matrix if it is for the scalar field from Rn to R. Okay, so it is defined by this. It is a matrix, is an n cross n matrix, so it should have n elements. The first will be my function f, my scalar field f is differentiate with respect to 1 and again with respect to 1, then it is differentiate with respect to 1, then with respect to 2, with respect to 1, then with respect to 3, dot f with respect to 1, then with respect to n. Similarly goes for the second row, 2 comma 1, f2 comma 2, f2 comma 3 and dot till f2 comma n, right? Similarly goes till the last row, it is n comma 1, fn comma 2 and dot fn comma n. Okay, so here we learn that my Hessian matrix is a n cross n matrix where the entries are given by this second order partial derivative. Hence in the statement I have wrote my second order partial derivative should exist, and there is one more extra condition. That extra condition is this partial derivative must be continuous. Now while learning in the chapter unit number 2, we have learned that if my second order partial derivatives are continuous, then the mixed partial derivative are equal. Hence I can write that since my second order partial derivative are continuous, hence my f1 comma 2 is same as f2 comma 1, or more precisely or in general I can write my f of I comma j is same as f of j comma I for all I and j in the range from 1 to n. Correct? Okay. So we learn that if I write 1 comma 1, if I write 1 comma 2, or I write f2 comma 1, answer is same. That means I got to know these two things are same, f1 comma 2 and f2 comma 1, means the order is not important. With respect to 1 you are differentiating first, or with respect to 2 you are differentiating, your answer will be same. Similarly, if you see this, the answer will be same as the entry over here, this over here, that will be f3 comma 1. Similarly, this is same as this, right? Similarly, this will be same as this matrix, this entry. Hence you can see, if this is the case, if my fij is same as fji, then I know that if I just make a transpose of this, my answer will be same. Correct? If I just make a transpose of it, transpose is nothing but changing rows to column and columns to rows, hence still my answer will be same. The only reason is my fij is same as fji. Correct? Hence I can conclude that my hf is a symmetric matrix. Okay, so note these things down, because for the MCQ point of view, the small points are really important. First of all, if my F from Rn to R, then the dimension of a Hessian matrix is n cross n. Then Hessian matrix entries are nothing but Fij, right? In the form of the matrix, if I want to write, I can write it as F. HF is nothing but matrix form Fi comma j, correct? And it is n cross n matrix. Also, I know that Fij is same as Fji. Hence, my Hessian matrix is always a symmetric matrix. Symmetric means what? Symmetric means my HF transpose is same as HF. Okay. So we are just learning the concept of Hessian matrix now. Then we will apply in the later on cases. I will solve example. Don't worry about it. But for now, let us just understand the concept of Hessian matrix. Okay. Now let me just think about Hessian matrix bit more. If you observe over here, this Hessian matrix is somehow related to my Jacobin matrix. Let me see how. In the Hessian matrix, we apply on the scalar field, right? And Jacobin matrix, we work on vector fields. But I know that my scalar field is somewhere related to vector field by using gradient. That means, suppose if my F is from Rn to R, then my gradient of F will be from Rn to Rn, correct? Where my gradient of F will be what? It will be nothing but partial differentiating F with respect to the first variable, partial differentiating F with respect to the second variable, and dot dot dot, the last entry will be partial differentiating F with respect to last, that is nth variable, right? Okay, this Rn to Rn. Just note it down now. This is also an important point. If I have a scalar field, the gradient is nothing but a vector field. Okay. So for now, how it is related to Hessian and the Jacobin matrix, I want to think. So now this is nothing but what? This is nothing but my vector field, and I can find out Jacobin for the vector field. So let me just find out my Jacobin of this gradient of F, which we actually write it as df, but I am writing J since I want to differentiate between Hessian and Jacobin clearly. Okay, so this means Jacobin of this. Okay, so now all of us knows how to find out Jacobin matrix. So Jacobin matrix is found by, okay, it will be what dimension? It will be from n cross n, right? So it will be n cross n. Then what I do is I just write the first function in the first row. So it is fx1 dot 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 fx1. The second function in the second row, x2 fx2 dot 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 fx2, entire that. Then at the end I will let fxn fxn. I write this. Then what I do, I just go column wise now. Now in the column wise, I should differentiate this with respect to first variable, this with respect to the first variable, this with respect to the first variable, second के अंदर second, second के अंदर second, and the last के अंदर with respect to the last variable, right? So if you observe this, the Jacobin of the gradient is actually same as my Hessian. Since you see the first term is nothing but fx1, again differentiating that with respect to x1. Hence, this matrix is same as what? This is same as the first entry is nothing but f, differentiate with respect to the first variable, and again with respect to the first. This is first variable, then with respect to 2 dot 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 f1n. This will go till the last row, that is n, then 1, then fn comma n, and that is nothing but same as my Hessian of f. Hence we found out a relation between the Hessian matrix and the Jacobin matrix. So let me just state it over here. The Hessian matrix of the function f is the Jacobin matrix of the gradient of the function f, correct? Also we note that my Jacobin matrix is for the vector field. These are the simple difference the student should note. Jacobin matrix is defined for a vector field, and my Hessian matrix is defined for the scalar field. Okay, so now I know there are so many difficulty and doubts, so be free. You can ask me in the comment section. If you have my number, you can WhatsApp me. The way you want to ask, you can ask. I have written page numbers. So on each page, means on the section, I have given the page number. So when you are asking doubt, you can be more precise where you have a doubt, right? So But for before starting with an example, let me just say what my Hessian is. Hessian is nothing but F11, F12, F13, F1n. Second row is F21, F22, F23, F2n, and so on. But I know there is one more easy way to find out this Hessian. That is what? First I will find out the gradient. Then of that gradient, I will find out the Jacobian. And hence that Jacobian will nothing but my Hessian matrix. We can directly do that. But since it makes us easy to go by the way of the gradient, correct, it looks more good and it makes easy for us. Otherwise you can directly find out all the second order partial derivative and you can work on it, no problem. Okay, but let me just say do these two examples which will help you to understand the idea of an Hessian matrix more better. Definitely we haven't learned the application of an Hessian matrix yet, but later on in this class only we will learn some application of an Hessian matrix. Okay, but note that Hessian matrix is for scalar field. Okay, so now what I say is I want to find out Hessian matrix for this. So I know what are the steps. One way is I should find out F11, F12, all that 9 entries I should find out. And other way is to go by the way of the gradient. I feel that is really easy. Okay, so I'll just find out the gradient of f. Okay, so what is the gradient? It is nothing but partially differentiating f with respect to x, then with respect to y, and then with respect to z. Okay, so if I partially differentiate this with respect to x, I will get answer as 1. If I partially differentiate this with respect to y, I will get answer as 1. If I partially differentiate this with respect to z, I will again get my answer as 1. Correct? Now I will find out Jacobian of this. Okay, it was so easy. It is Jacobian of this. Okay, Jacobian of this gradient is nothing but my Hessian matrix for f. How I find out Jacobian? I need to write the entries in a row. That means it is actually 1. So I will write 1, 1, 1 everywhere. 1, 1, 1, 1, 1. Okay. Then after that, first row I will differentiate with respect to x, x, x. Over here I should differentiate with respect to y, y, y. Over here also y, y, and sorry, over here it should be z, right? The last row should be z. It is z, z, and over here z. But since there are no variable anywhere, I see it is nothing but 0, 0, 0, 0, 0, 0, 0, 0, and 0. Hence, my Hessian matrix for the given scalar field is nothing but 0. 0 matrix, right? This is nothing but a 0 matrix. Okay. Now we are learning about how to find out. We'll use it definitely. But if you have any doubt, difficulty, just let me know in the comment section. Okay. Now we'll see one more difficult one. So over here I am supposed to find out gradient. So by gradient of f will be, first element will be partially differentiating this with respect to x. Okay. So log x derivative with respect to x is nothing but 1 by x. Over here there is no x, hence the derivative is 0. Plus over here the third term will be partially differentiated with respect to x, it becomes e raised to z. Then with respect to y, if I differentiate this entire one, I'll get answer as z. If with respect to z, I differentiate this entire one, I get my answer as y plus e raised to zx. Correct? So this is nothing but my gradient. If I want to find out the Hessian for this, what I'll do is, I'll just find out my Jacobin matrix for this gradient of f. Correct? So this is same as, I'll just write the first one. Here it is 1 by x plus e raised to z, 1 by x plus e raised to z, 1 by x plus e raised to z. On the second I should write z, z, z. On the third I should write the third one, that is y plus e raised to zx, y plus e raised to zx, and y plus e raised to zx. Okay. Now what I will do is, I'll just partially differentiate first column with respect to x. Okay. So in exam, if you have just an MCQ exam, don't go to find out entire one. Just find out few entries and just verify which one of them is satisfied. Okay. So this with respect to z, this with respect to z. Okay. So now it is easy. Okay. So if I differentiate this partially with respect to x, my answer is nothing but minus 1 by x square. If I differentiate this with respect to y, my answer is 0. If I differentiate this with respect to z, my answer is e raised to z. This with respect to x is 0, this is 0, and this is 1. This with respect to x is nothing but e raised to z. This with respect to y is nothing but 1. And the last entry with respect to x, will be same as, sorry, with respect to z will be same as e raised to zx. Okay, so this is nothing but my Hessian for f, right? So simple, correct? So I will request my student to solve some of an example as a practice. Okay, if you cannot do it, don't worry about it, I am always there for you, but I feel you guys will learn about it once you do the example. Okay, so there's literally simple example. Okay, I have just put how many, 1 2 3 4, this all are 2 cross 2. Okay, if you want I will just solve first one. This first one I'll just give you a hint. For the Hessian for this, you will find out gradient of f, correct? X comma y will be this, over here there will be f of x, over here there will be f of y. Then you will find out the Jacobian of gradient of f, you will call it as your hf. This will be a 2 cross 2 matrix, 2 cross 2 matrix, where the first will be fxx, here it will be fxy, fyx, fyy. Okay, one more thing that we have forgot to do is, we just forgot to verify that our matrix was a symmetric matrix. You can observe over here, this hf is nothing but a symmetric matrix. Over here also, if you observe, if I do transpose of this, I get the same matrix. Okay, what is the reason behind this? Since over here we will considering those example only where my second order partial derivative are continuous, hence my Hessian will be a symmetric matrix. You can observe here, if you take a transpose, this is same as this, the last entries, all the entries are same, right? The rows, if you change by column, you get the same matrix. Okay, the same will be true for others also. Okay, so I'll just request my students to do this 4 example, note it down and do it. Okay, if you cannot do it, don't worry, I'll help you out. Okay, so just note this down. Okay, sorry, that went up, sorry. Okay, it should go up, I think, otherwise I'll just show you. Wait, sorry for the inconvenience, but I think it will come now. Yes, so these are your 4 example. Okay, I'll request you to pause the video and then do it just now only. Okay, then you can move forward. Okay, now we'll be learning one more new topic. Okay, let me just change my page. Okay, now we'll be learning about extrema. Okay, I know you guys have learned about it prior to this when you were in SYBSc, right? SYJC, that means 12th. When you guys were in 12th, you guys have learned about this, but for f from R to R, extrema, from the word itself, you can guess what we are going to learn, right? So extrema means what? We will be thinking about where my function is attending its extremum value. Extremum value means where it is maximum, where it is minimum, what is its minimum value, right? When you guys were learning derivative in 12th, inside application of derivative we will learn this. The same thing we will be learning for the scalar field. Okay, so before starting with the theory that I have wrote, don't read that. First of all, I will just revise what you have done in R to R case, right? So if my f from R to R, then what you used to do is, you just used to take a derivative of f and just equate it to 0, correct? You will get some values of x, right? X naught. Suppose if my derivative is 0 at the point x naught, then you say that my x naught is the critical point. Critical point. What is the meaning of the critical point? That means that point can be either my maximum point for the function or it could be my minimum point for the function. Over here, one more thing that we should notice, if you see the derivative equal to 0 at that point means what? That means if I just try to explain in terms of a graph, so let me just put a small graph over here. Okay, suppose this is my x-axis, this is my y-axis. Suppose if my function is like this, okay, and if I find out derivative at this point, derivative is nothing but what? In case of R to R, my derivative is nothing but slope of tangent at that point. Means this thing represent my slope. If this is my f of x, this function is f of x, then this represent slope of tangent at x naught, correct? Means at that point, if I draw a tangent, the slope of the tangent should be 0. Suppose if this point is nothing but x naught, then the slope is 0 means what? Means this line is nothing but parallel to my x-axis. Correct? This, whenever your tangent is parallel to x-axis, means that point is nothing but a critical point. Critical point means what? It will be either maximum or minimum in its neighborhood. Correct? Okay, so we learn about it in 12th. The same idea I'm going to generalize for the scalar field. Okay, so let me just revise that idea or extend that idea to the scalar field. So I just read the theory that I have wrote. This thing already we have discussed in unit 2 when we were learning tangents. Okay, but still if you have any doubt, difficulty, be free to ask me. But let me just read what I have wrote. So first I have wrote a surface that is described by this. Okay, so you can observe my input is, my f is nothing but from R2 to R. Okay, so this is nothing but, if I just try to draw a graph, it will be a 3-dimensional graph. Over here from R to R my dimension was 2, right? It was 2-dimension graph. Over here it will be 3-dimensional graph. We are learning in 3-dimensional graph only because we cannot visualize other things. Otherwise the same idea could be generalized in higher dimension also. But we will be learning in SYBSc for a function, a scalar field from R2 to R. Okay, so if suppose they have given me this surface, then the level surface for this could be defined as by capital F xyz is equal to fx comma y minus z. This thing we have done when we were learning about tangent plane, right? So if the function is given as z is equal to x square plus y square, we used to do 0 is equal to x square plus y square minus z, and then we used to think about the tangent. The same idea we are applying over here. So I consider f is equal fx capital F xyz is equal to fxy minus z. Then I just find out gradient of it. So if I just differentiate this with respect to x, it will be fx, means partially differentiating this f with respect to x. Since over here there is no x, it will become 0. Similarly it is fy if I differentiate entire with respect to y. Now if I differentiate entire with respect to z, my first function is independent of z, hence it becomes 0. And if I just differentiate this much, it will become minus 1. Okay, so I just find out gradient of this capital F, which is nothing but my level surface. Okay, so now if I want to find out tangent at the point P1, which is nothing but x1, y1, z1, then we know how to find out tangent for the level surface. What we used to do, we used to take a inner product. We used to take an inner product of f at the point P1 with x bar minus P1 is equal to 0. You can interchange this if you want, but this was nothing but an equation to find out the tangent, right? So the same equation I have wrote below it. Here if you see, my gradient of f at the point P1, inner product with P1 minus xyz, which is equal to 0. Okay, so now what is my gradient? My gradient is nothing but fx fy minus 1. This P1 minus xyz can be written as this, right? If I take an inner product, I should multiply first entry with the first coordinate, second coordinate with the second, third with the third, right? Hence I get this. Here I have wrote this. If you observe, why I wrote partial derivative at x1 and y1 only? Since we are supposed to find out gradient at the point P1, where at P1 my x and y coordinates are this, correct? Hence I wrote my partial derivative at the point x1 y1. Since I wanted my gradient at the point P1, and in P1 my x and y coordinate are x1 y1, hence I wrote this. Okay, so now if you observe, this is nothing but what? This is nothing but my equation of tangent. Equation of tangent, correct? Now if I just have my this fx, means this partial derivatives, this fx and fy at the point x1 y was 0, then what happened? Suppose if my partial derivatives are 0, then my equation of tangent, if this entire things become 0, then the equation of tangent become my z1 minus z is equal to 0. That is nothing but my z is equal to z1, right? So it becomes my z is equal to z1. Okay, so I just mark this. This is nothing but z is equal to z1 is nothing but my equation of a tangent when if my partial derivative are 0. But if I say my z is equal to z1, that means my tangent is parallel to xy axis. Oh, this is something similar that we have learned in R2R case. Whenever my tangent is parallel to x plane in R2R case, I say that my point is nothing but a critical point. So similarly, when my tangent is parallel to xy plane, that means my tangent is nothing but z is equal to z1, that is nothing but my partial derivatives, are 0, then I say that point is called as a critical point, since that point can be either maxima or minimum. But for now we will call that point as a critical point, or the other name for it is nothing but a stationary point. Okay, so this entire theory is just to explain you that whenever my partial derivative with respect to x and y are 0 at a point, then that point will be called as a stationary point or the critical point for that function. Why we call it as a stationary point or a critical point? Because if the partial derivative are 0, then my tangent plane will be parallel to xy axis. Correct? You can observe we have just generalized the R2R idea to R2 to R idea. Correct? When we have R to R function, then we have converted that idea to R2 to R function. Correct? So the same idea we are generalizing. Okay? So this is nothing but the theory. Let me just see some more definition that will be required to us in this course. Okay? So if you have any doubt, difficulty, be free to ask me. Okay? Not to worry about it. I will just revise all the things again in the class, but not in detail. Okay, let me just give you the more definitions now. You can see this filling the blanks because I just wanted to save time, but this cursor is not helping me to save the time. Okay, I think it is enough. Okay, so we just note it down. The point P1 will be called as a stationary point of the surface, where is P1 के अंदर क्या था? On that P1 we have x1, y1, z1. But actually we are not so interested in the point z1. Since my input is from R2, we are just interested in x1 and y1, right? So this x1, y1 will be called as a stationary point or the critical point of that function. This P1 comes in a play if I am talking about a level surface, but I am not interested in a level surface. I am just interested in my scalar field, and in the scalar field I have only 2 dimensions. Hence we just talk about this x1, y1. Okay, the P1 comes in the play if I am talking about level surface. If I just want to think about my scalar field, x1, y1 values are enough for me. Hence my x1, y1 value where my partial derivative are 0 are called as a stationary point of the critical point. Okay, so there is one more note that we should make. We actually made it earlier. Let me just note it down. But okay, so note will be the tangent plane is horizontal. That means I just wanted to say it is parallel to xy plane. Okay, it is parallel to xy plane at the stationary point. We have already wrote it is parallel to xy plane earlier, but this is nothing but a note. Why it is at a stationary point? What is a stationary point? A stationary point is a point where my partial derivative with respect to x and y at that point are 0. Means at that point my tangent plane will be horizontal. That means it is parallel to xy plane. Okay, these stationary points are important because they are the point where my function could be either maximum or minimum. Okay, so I just write the definition of maximum and minimum, but let me just scroll down a bit. Okay, the stationary point of the surface are usually classified in 3 categories. Okay, so prior to this you have learned about 2 categories. In this course we will be learning about 3 categories. Okay, so just note it down. There are 3 types of stationary point. The first one we call it as maxima. From the name itself we can guess that at that point, at that stationary point, my function is maximum. Second is called as a minima. Okay, and the third will be called as a saddle point. Don't worry about it if you don't know about the saddle point. I'll just explain you in a detail, but the first 2 are extremely clear. Maxima means what? At that point my function is maximum. Minima means at that point my function is minimum. Okay, not to worry about it. But let me just define the word maxima in the scalar field. Okay, so scalar field F is said to have an absolute maximum. I'll just write have absolute maximum at a bar of a set S in Rn. Maxima means what? At that point my function should attain maximum value. If my f of x bar is less than equal to f of a bar for all x bar inside that set S. Okay, so that means what? I'm just trying to say my f of a bar is a maximum value which is attained by my function in that set S. If I'm talking about the entire set, then I will call it as an absolute maxima. Okay, so note it down. If I'm talking about the entire set, then I will call it as the absolute maxima. Before that, before moving forward, I'll just let you know the number, the maximum number attained by my function is nothing but f of a bar, right? Is called the absolute maximum value. Is called absolute maximum value of f on S. Okay, it's really trivial. So there is one more type of maxima that we should discuss. Over here we discuss about absolute maxima. Now we will be thinking about relative minima. A scalar field F is said to have relative minima, or sorry, relative maxima over here I should have write maxima, okay, at a bar if the condition is similar. That means my f of x bar is less than equal to f of a bar for all x bar inside the ball b a bar, where this b a bar is ball is for some n ball a bar. Now let me just explain the difference to both, all of you. So the absolute maxima means what? I am talking about the entire set. When the word relative is used, we are just trying to say that in the neighborhood of that point. That means I can say that my a bar is nothing but relative minima if in that neighborhood my function is maximum. Okay, let me just try to explain in terms of a graph that will be more clear. Okay, so suppose, okay, I'll just take this. Okay, so suppose I talk like this is my function. Okay, so this point can be said as a relative minima because in its neighborhood I can see that is a maximum value, but for the entire graph this is not a maximum value, correct? So this is nothing but a relative maxima. Again, this is nothing but a relative maxima because in the neighborhood it is maximum, but not for the entire graph. Okay, but if I observe this point will be my relative minima also as well as my absolute maxima also, because this is nothing but my maximum value attained by my point. Hence my this point is nothing but my absolute maxima. Okay, this input point will be called as an absolute maxima point. Over here this input point will be called as a relative maxima point, and that value will be called as an absolute maximum value. Over here whatever the value my function take will be called as an absolute maximum value. Okay, so the difference between relative and absolute is clear. I think it is actually simple, but if you still don't get it, don't worry about it, just ask me in the comment section. I'll just explain in detail. Similarly, we can define about absolute minima and relative minima. Okay, similarly you can define about both of this. Now time comes to think about saddle point. Okay, so let's think about saddle point. Clearly student can actually guess what should be a saddle point. Now we already discussed the maxima minima, so point which is neither maxima nor minima, such a kind of a stationary point will be called as a saddle point. Okay, so let me just write the definition, then I will show you 4 example graphically. But before that, let me just write the definition of a saddle point. Okay, So I'll just write in detail because the saddle point is really important. So assume my f is differentiable at the point a bar. If my gradient of f of a bar is equal to 0 bar, अगर मेरा gradient at that point is 0, that means my partial derivative are also 0, because gradient is nothing but made up of partial derivative. Hence if I say my gradients are 0, hence I want to say my partial derivative are 0. Hence the point a bar is called stationary point of f. Okay, now first of all I just defined stationary point, which we have already done, so I just wanted to define it again in terms of the gradient. Now what I will define a saddle point. So a stationary point is called a saddle point, if every n ball, every 2 ball, because we will be discussing in 2 dimensions, I just write 2 ball, every 2 ball, 2 means 2 dimension, 2 ball b a bar, I just write b a bar, it is 2 ball denoted by b a bar, contains a point x bar such that that f of x bar is less than f of a bar, and also contain another point such that my f of x bar is greater than f of a bar. That means I am trying to say that there exists a point in the neighborhood of f of a bar, irrespective of whatever neighborhood you take, right? There always exist points where the function is taking higher values also and the function is taking lower values also. That means my f of a bar is neither a maximum value nor a minimum value. Such a point will be called as a saddle point. Note one thing, the point must be stationary point first, then only we think about saddle point. अगर आप कोई भी पॉइंट लेके आओगे फिर बोलोगे सर ये सेटल पॉइंट है कि नहीं, फर्स्ट ऑफ ऑल यू शुड चेक इज इट अ स्टेशनरी पॉइंट, देन ऑन वी टॉक अबाउट सेटल पॉइंट्स. ओके, सो नाउ इट्स टाइम केम to think about 4 examples. Okay, we'll discuss 4 example graphically. Okay, so I just went to a site where here I had just already written 4 examples for all of you. The first one that we'll discuss is this. Okay, if you see this function, this is nothing but a function z is equal to 2 minus x square minus y square, right? So this is nothing but a 2-dimension function, right? So it is from R2 to R, hence the diagram, the graph is nothing but inside R3, right? So if you see over here, this function at this point 2 have the tangent which is parallel to my xy plane. This plane is nothing but an xy plane, hence at that point my all the partial derivative with respect to x and y will be equal to 0, correct? Also you can note that at this point, means at 0 comma 0 my function is attaining its maximum value, which is 2, correct? Hence I can conclude my 0 comma 0, first of all it should be a stationary point. Why it is a stationary point? Because at that point, because at this point 0 comma 0 my tangent plane will be parallel to xy plane. Also that stationary point is a maximum because my function, if you can see on the graph, my function is attaining a maximum value at that point, correct? So this is nothing but an example, z is z minus x square minus y square. This is nothing but a graph. In that graph we can easily see that my 0 comma 0 is nothing but a maxima. First of all it is stationary point, then it is maxima. Okay, let me just give you another example. This second one is nothing but z is equal to x square plus y square. If I just draw this graph, it will be like this, a parabola, 3D parabola, right? Okay, so you can see over here my function has a tangent as an xy plane itself at the point 0 comma 0. Hence at 0 comma 0 my tangent will be xy plane, hence it is parallel to xy plane, hence my 0 comma 0 is a stationary point. and also from the graph I can conclude that my function is attaining its minimum at that point. Hence my 0 comma 0 is nothing but a minimum, correct? The one way to think about the stationary point and maxima minima is by going through a graph. Okay, at the end of this class I will show you without thinking of the graph how we can do that about is the point is maxima or minima. We can do that, right? But for now let us just see by using a graph. Okay, so 0 comma 0 is a stationary point where my function is minimum. Okay, let me just go for the third graph, that is z is equal to xy. Okay, I think okay, but this is nothing but something else only. No, this is not xy, this is something else. If I just go for this it will become difficult, so I just won't take this example. I have to take the other example, right? Okay, yes, this is that example. If you can see, yes, you guys can see clearly about this example. I'll just zoom it a bit because I just want to see where my origin is. It is okay, yes, we can see. I just wanted to zoom it. Yeah, okay, I can go it with this. Actually I just wanted to give you an example of a saddle point, right? Saddle point means such a point where my point is neither maximum nor minimum, correct? It should neither be maximum nor should be minimum. Okay, I just wanted a good example. Actually this is not, no, z is equal to xy. It should have came a good graph actually. No worry, actually one of them should be, actually this is a good graph but I am unable to zoom at the center of it, which is a problem for me. Okay, relax. Yes, this is good. Okay, now I can see the origin actually. Yes, I need to go below the origin. Extremely sorry for the inconvenience, and you can ignore the background sound for now. Okay, so yes, you can see over here my function at the point origin. At origin, if you observe the graph at the origin, you can observe my function is neither minimum nor maximum. Since if you see in this dimension, on the my y-axis dimension, it is increasing, but if you go in terms of a x-axis, it is decreasing at that point, correct? So in one way it is increasing, in the other way it is decreasing, correct? If you see at that point, it will neither be maximum nor be minimum. I'm extremely sorry about the noise. I cannot do anything. I can just wait for 2 minutes, nothing else I can do. Okay, so I just don't want to pause the lecture. Okay, so now I think now he won't cry. Okay, extremely sorry, but we can continue. Okay, so no worry about it. Okay, so now he's fine. Okay, so great. So now I can observe in such a graph, if I see at the origin there is a curve in both the direction. Means if I go in the y-axis direction, it is increasing, but if I go in the x-axis direction, it will go on decreasing at the origin. Hence at the origin I can see that it will neither be a maxima nor be a minimum. Don't worry about it. I'll give you more example later on about the saddle point, because I can clearly see now the diagram is not so good in representing what I actually wanted. If I just no over here also, if I see, yeah, this is good, this I can explain really well. Yeah, this is good. Okay, this is really good example. This is actually like a saddle. What is a saddle actually? The saddle is nothing but a shape which you can see on the horse, right? If you see the horse seat, suppose if you, this is a horse back, then the horse seat is like this, right? I should make it a more curve. So suppose this is nothing but his back, horse back. So if you see, it's something like this, right? So if you observe it in this direction, if you put a ball over here, it will come down, but if you put a ball over here, it will come like this, correct? So if you go in this direction, the points are increasing, but if you go in this direction, the point is decreasing. Hence at that point, if I consider this point, at this point if I consider any neighborhood, there will be some points where my function is greater than it, and there will be always some point where my function is less than it, correct? The saddle is nothing but this kind of a shape of seat on a horse, and actually this is nothing but an example of it. If you see in the different directions, so if you see over here, it will come down like this, and if you go in the other direction, it will go down again. So this all are maximum than greater than my function at the 0, and the rest of the point, if I go in the other direction, they are minimum or lesser than the point at the origin. Okay, I hope I was trying to explain it really well. Actually, I just got confused when it came to the bigger shape. In the smaller shape, it was really simple, which I show it over here, right? So I hope the saddle idea is a bit more clear. But what we can do is, after this, we can go for an actual example which will help you to get a clear concept. Okay, so the examples are really simple, I will say. We guys have already learned about this in R2R case. So what I'll do, I'll just give you an R2R case and then I'll just generalize that idea. Okay, just wait for a few more minutes and that will complete this video. I'll request student to go for the entire video, please. Okay, so my second derivative test for R2R case you have already learned. NTY. Let me just revise this. I know, sir, एक साल पहले का नहीं पता, आप 2 साल पहले की बातें कर रहे हो. So I'll just revise this. Don't worry about it. Okay. So my f from R2R. So what we do, we first find out the critical point. So my f dash at the point x naught is 0. Then we call x naught is the critical point. Critical point. Correct. And after find out the critical point, what we used to do is, then we consider two cases. If we find out the double derivative at the point x naught, and if the double derivative is less than 0, then we conclude that my x naught is minimum point, minima. Correct? Means at that point my function will be minimum. And second case was, if my f double dash at the point x naught is greater than 0, sorry, I just went the other way around, actually that noise just interrupted me. If it is less than 0, then x naught is my maxima. Okay, note that it is maxima. When it is less than 0, it is maxima. When it is greater than 0, it is minima. Okay. Okay, so we'll just generalize same idea for the scalar field. But for the scalar field, finding out double derivative, no, we won't do it. We will just go for the Hessian matrix that we have learned in this video. Okay, so let my a bar be the stationary point of a scalar field f. So first of all, we will consider a stationary point and we want to find out an Hessian, right? So to find out Hessian, we should have a continuous second order partial derivative in two ball b a bar. Means at some ball it should have a continuous second order partial derivative. I know you guys have not to worry about it, because whichever question we'll be discussing, this will be satisfied for sure. But you should know the required basic condition. Okay, so after this, what we do, I'll just give you the test for it. Okay, this is nothing but a second derivative test for R2R function. I will give you a second derivative test for the function which is from R2 to R. Okay, so the test required an Hessian matrix. So let me just give you that. So let my delta be equal to determinant of the Hessian matrix at the point a bar, and we required one more thing, that is nothing but my h11 at a bar, that we usually denoted by a. H11 at a bar means what? That is nothing but the first entry in this matrix. That is nothing but my fxx at a bar. Okay, so if you know these two things, the test is concluded by using this two value. The test says that if your this delta, which is nothing but determinant of the Hessian matrix at that point a bar, if it is less than 0, then my f has a saddle point, at a bar. If my this delta is greater than 0 and this my a, that means nothing but the first coordinate, is also greater than 0, then my f has relative minima at a bar. Okay, so both are greater than 0, then it is minima. Similar to over here, if it is greater than 0, it is minima. So similar cases over here, if both of them are greater than 0, then it is minima. But if my delta is greater than 0 and my a, that means first coordinate, is less than 0, then f has relative maxima at a bar. Now the last case is nothing but where my delta is equal to 0. It might be possible that my determinant is equal to 0, right? Then the test is inconclusive. Means we cannot conclude anything if my determinant is coming out to be 0. Then the test is inconclusive. Okay, so this is nothing but a test. I will request students to read it once, note it down, because we will be using this test now. Okay, I will just solve one example in which I will just using this test. First of all, we will be finding out the stationary point. Then I'll just use this test to classify the stationary points. Okay, so this is the test. What we want a stationary point first of all. Then we want a Hessian at that stationary point. Find out the determinant of it, that is nothing but a delta, and based on the value of delta and the first coordinate in the Hessian matrix, we can conclude that my stationary point is a saddle point, maxima or minima. Okay, we can conclude about it. Okay, let me just give you an example first. Okay, a bit more up. Okay, so locate and classify. Let me just go to the full screen now so you guys can see better. Okay, so locate and classify the critical point for the following example. Okay, so first thing I need to find out is the critical point, that is nothing but stationary point. To find out the stationary point, I know I should find out the gradient first. Okay, so I'll just find out the gradient. So my gradient of f x comma y is equal to, so gradient is nothing but partially differentiating this with respect to x is nothing but my 4y plus 4x cube. This with respect to y is nothing but 4x plus 4y raised to 4. So my gradient will be when, if my my stationary point or the critical points are the point where my gradient is 0. So my gradient of f, I will equate it with the 0 bar. Correct? That means I will consider my first coordinate as equal to 0 and my second coordinate also equal to 0. Okay, hence from the first equation I can write my y is equal to minus x cube, and from the second equation I can write my x equal to minus y cube. Okay, so what I can do is I can use one value in the other one. So if I have x is equal to minus y cube, I have y is equal to minus x cube. So I'll just use equation 1 in 2. Correct? That means what? That means my x is equal to minus, on the place of y I can write minus x cube whole cube, that is nothing but minus, so minus cube is nothing but again minus, hence it will be what? It will be nothing but my minus x raised to 9, hence it is but x raised to 9. Okay, so my x is equal to x raised to 9. So I need to think about all those points which satisfy this equation. Definitely my x can be equal to 0 will satisfy this, x equal to 1 also can satisfy this, also my x is equal to minus 1 can also satisfy this. Okay, so I got 3 values of x, and correspondingly I can find out the value of y from the equation number 1. Okay, so therefore when my x is 0, by equation 1 my y is also 0, my x is 1, then from equation 1 my y is also minus 1. If my x is minus 1, then by equation 1 my value of y will be 1. So these 3 are the points where my gradient is 0. Means these 3 are stationary points. Okay, so these are nothing but a critical point, which I also call as a stationary points. Okay, now we need to classify them. To classify them I need to use a second derivative test. That means I need to think about the Hessian matrix. How to find out the Hessian matrix of f? Hessian matrix is nothing but my Jacobin of the gradient matrix. Okay, so the Jacobin is nothing but what? It will be a 2 cross 2 matrix, because my function f is from R2 to R. My Hessian will be a 2 cross 2 matrix. Correct? Okay, so first to find out the Jacobin I need to write the first one. So I'll just write the first in the first entire row, 4y plus 4x cube 4x plus 4y raised to over here it should be cube यार, है ना, यहाँ पे क्यूब होना चाहिए था, हमने यहाँ पे गलत लिखा, नीचे सही लिखा, so I am so smart. So it is 4x plus 4y cube. Now in the first column I will differentiate with respect to x, in the second I will differentiate with respect to y. Okay, I just write it over here. So this is nothing but what? This is, if I differentiate this with respect to x, it will become 12x square. Here if I differentiate this with respect to y, it will become 4. This is again 4. If I differentiate the last one with respect to y, it become 12y square. Okay, so first of all I am supposed to find out for 0 comma 0. Okay, so I'll just go for 0 comma 0. For 0 comma 0, my hf at 0 comma 0 will be same as what? Means on the place of x I should write 0, on the place of y I should write 0, hence it becomes 0, 4, it is 4 and 0. Okay, first of all I will find out the delta, that is nothing but determinant of this, that is nothing but determinant of hf 0 comma 0. So what is the determinant of this? This is 0 minus 16, that is minus 16, which is less than 0. So whenever this delta is less than 0, we are not worried about anything, because this implies me my 0 comma 0 is a saddle point. Correct? It is a saddle point. Okay, so at that point it is nothing but a saddle point, means 0 comma 0 is a saddle point, means at that point my function is neither maximum nor minimum. It will give me some shape like a saddle at that point. Okay, so let me just go for the second, that is 1 comma minus 1. So for 1 comma minus 1, what I need to do is I need to find out Hessian at that point 1 comma minus 1. So that is same as what? That is same as at the point of x I should write 1, that is nothing but 12, 4, 4. On the place of y I should write minus 1, so it is again 12. Okay, so I just need to find out the delta value, that is nothing but determinant. So it will be 12 square minus 4 square. Definitely it will be greater than 0. I am not worried what the value is. Also you can observe my first entry a, that is nothing but 12, which is also greater than 0. Hence if both of them are greater than 0, then therefore my this 1 comma minus 1 is a minima. Correct? If both are greater than 0, then it is a minima. Similarly, for what was the third point according to me? I think it was minus 1 comma 1. Right? It was minus 1 comma 1. At that point again my hf 1 comma minus 1 will be the same matrix, because I need to square them. So it is 12, 4, 4, 12. Hence again my delta value is greater than 0 and my value of a is greater than 0. Therefore this minus 1 comma 1 is also minima for my this graph. Okay, so now time comes to just verify this idea and let's see how the test is working well. Okay, so now I know 0 comma 0 is nothing but a saddle point, 1 comma minus 1 is minima, minus 1 comma 1 is also minima. So let me just see the graph of it. Okay, if I just go for the graph, this is nothing but my function if you observe carefully. Right? So it is 4xy plus x raised to 4 plus y raised to 4. And if you just observe the graph, okay, I just need to, okay, now it is fine. Yes, I need to zoom it up, okay, a bit. Okay, yes, now it is fine. So yes, you can observe at 0 comma 0 it is making a shape like a saddle, right? So it is neither maxima nor minima. And you can observe at the rest 2 point are nothing but over here. If you see the legs of this, it's like something like a pent, but you can see the legs of it are nothing but the 2 other minima points, that is 1 comma minus 1 and minus 1 comma 1. These are nothing but these 2 points. The image will be over here. Correct? So this is nothing but a graph, and we can clearly see there is no maxima point. There are only 2 minima in that one saddle point which we found, right? So this is nothing but a graph, and this is how we have used our second derivative test. Okay, there is one more example for all of you to solve. Just try to solve that example, and this is nothing but the third example. I'll just show you on the screen. Just note this down. This is the third example, which is an exercise for all of you. And I feel question number 2 is also much simpler than what we have done earlier. You guys can try the second one also in the similar pattern. If you have any doubt, difficulty, ask me in the comment section. But thank you so much guys for watching this video till the end. Okay, if you have any doubt, difficulty, you can ask me the way you want. You can write in the comment section whatever you want to do, you can do, right? But you can ask me freely. I'll just solve your doubt as soon as possible. Okay, so thank you so much guys for watching this video till then. Okay, chalo, bye bye.